thank you very much for the introduction. It's very great to be back here. I clearly did not come prepared for the rain since I only have one pair of shoes, so I'll be like walking around kind of with soggy feet, but hopefully that won't affect the talk. Okay, so everything I'm going to talk about today is joint work with Valentina Disarlo. And what we're going to talk about is somehow a new approach to understanding geometric triangulations on surfaces. Okay, but before we get into the geometric setting, let me just review triangulations in the topological setting. Okay, so let me begin with topological surfaces. Okay, and throughout this talk, let's just assume all of the surfaces are closed to make things easier. So I want connected finite type surfaces, but in what we do, we require that there exists a finite non-empty set of marked points. Okay, these are going to be the prescribed points where we're allowed to put the corners of the triangles. So I'll denote it like this: S, comma Z, Z being the finite set of marked points. Okay, so on such a surface, we can consider arcs. So what is an arc? An arc is just going to be some properly embedded segment, but I'm going to require that it doesn't self-intersect, and I'm allowed to do proper homotopy. So I'm allowed to wiggle it around without breaking it. Okay, so these are arcs, and if I've try to fill it in with lots and lots of arcs until you can't find any more, then you end up with a triangulation. So a triangulation is going to be a maximal collection of non-pairwise homotopic arcs, and once you fill such fill such a surface like this, you end up cutting the surface into triangulations. Okay, just so that things are meaningful. So if the genus is 0, I require that there's at least 3 marked points, because otherwise there does not exist a triangulation. Okay, so that's just a little thing we want to look at. Okay, so sorry?
Use 3 points. How many points do you need?
If the genus is 0, I need at least 3. Otherwise, I request at least 1. Okay, so just yeah, this set is always assumed to be non-empty. Otherwise, I can't talk about the endpoints. Yeah. Right. So yeah, so these are just topological. The interiors would be embedded, but I'm allowed to glue, the sides. I'm allowed to do something like this. For example, if I take the standard picture of a torus, this is the triangulation of a torus with 2 triangles. So that's perfectly allowed. Okay, so in this case, I would have to choose a marked point for the torus. Okay, and then if you take a maximal collection of non-crossing arcs, you cut it up into 2 triangles. Yeah. Okay, so associated to this sort of class of surfaces, there are 2 objects that crop up quite a lot in low-dimensional topology and geometric group theory, namely the arc graph and the flip graph. Okay, so what we do, the setup we do applies to both of these things, but today I'll focus more on the flip graph. Okay, so let me just recall what these are. So these are graphs. So the vertices will be the simple arcs. So arcs meaning no self-intersection. I require the endpoints to be at the marked points. They can have the same endpoint that's allowed. And this is up to proper isotopy. So proper meaning the endpoints need to be fixed throughout. And the edge relation is when they have disjoint representatives. So no transverse intersections. They're allowed to have maybe a common endpoint, but as long as they're not transversely intersecting, then this will be allowed. Okay, and you can make this as simple as complex by declaring any multi-arc. When you have pairwise non-crossing arcs, that spans a simplex. So a maximal simplex would be a triangulation. Okay, and the flip graph is the graph of triangulations. Okay, the vertices would be topological triangulations. So maybe I'll write topological because I will talk about geometric ones later. Of the surface, okay, and here with the requirement that I'm only allowing the edges to be arcs that go between these prescribed points, and the edges in this graph will correspond to flips. So what is a flip? This is a way of converting one triangulation to another. So if somewhere I see 2 adjacent triangles, like so. So these need to be distinct triangles. And so neighboring this arc would be two triangles, so it lives inside a quadrilateral. So what I can do is I can delete the diagonal inside and replace it by the other one. So this move is called a flip, okay? And whenever two triangulations are related by one, you put an edge between them, and then you can construct this graph that encodes all the possible triangulations on this surface. Okay, so as I said, like I want to focus more on the flip graph today. Okay, but just for motivation, if you're interested in the mapping class group, these graphs admit actions by automorphism by the mapping class group. The arc graph has been used quite a lot, and especially in, for example, if you're interested in fibered hyperbolic Fourier manifolds, you can get some information about the geometry of the Fourier manifold by computing certain distances in various arc graphs. So that's something that's this has been used for. The flip graph has been used to give some kind of nice cell decompositions of Teichmüller space. So that's also one motivation for this. But I'm not going to talk about that much today. I'm going to more focus, okay, well, analogues of the flip graph and an arc graph when you have some kind of geometry on the surface.
So the flip graph, like that flipping motion keeps the number of triangles constant.
Exactly. Okay, so for any triangulation of the surface, they always have the same number of triangles. And in fact, I'll call this the triangulation complexity is a well-defined number, okay, which is equal to the number of triangles in any triangulation of the surface. Okay, yes, yeah. So this is the fixed number. Okay, for example, that's 2. Yeah.
Is the flip graph always connected?
Yes. So I'll come and I'll sort of yeah. So I'll come to that, like, and not just connect it. I want to talk about how can you find, how can you actually produce a path as well. Yeah. So sort of the basic properties. So facts. Okay. So the arc graph is connected, locally infinite. So that means that the degree of every vertex is infinite. Okay, so if I give you one arc, then I can cut along it, and any other arc that lives on the sort of subsurface I get by cutting will be disjoint from the original arc, and you can get you can wind around how many times you like. So every arc has infinitely many neighbors, and it also has infinite diameter. So if you equip the graph with the standard graph metric where the distance between any two vertices is the length of the shortest edge path between them, okay, it turns out to be an infinite diameter graph. Okay, so these are some facts. Okay, and I'll talk about the flip. Oh, so I should always include the notation, which is I want the surface and the set of mark points. Okay, so this is also connected. But it's locally finite. Okay, because the flips come from whenever you have one arc and you change to something else. Okay, there's only like finitely many arcs on any triangle, any triangulation. So there's only finitely many moves, and it is also infinite diameter. Okay. So let me sort of say a bit more about this one, why the flip graph is connected. So I don't know what the first proof of this is, because it's quite, I guess, classic in this area. I think the first reference for connectedness would be Hatcher in 1999. Okay. But this is like sort of phrased in a different way, not especially referring to the flip graph, but related to something which is kind of equivalent to it. Okay. And then there was, but then we could get even sort of better connectedness. We can actually, if I consider the distance between two triangulations, so let's say T and T prime are two triangulations of the same surface, I want to know what's the distance in the flip graph. This turns out to be bounded above by the geometric intersection number of the two triangulations. So what does that mean? So if I give you two arcs, I can count the number of times they cross. So that's the intersection number of two arcs is you have to like pull them in the minimal position. So find the minimal position for any two arcs, and then just sum over all arcs T, sum over all arcs T prime, and just add those numbers up. So the total number of intersections, if you sort of put it into minimal position between these two triangulations, gives an upper bound for the distance. Okay, and it's not mysterious. It's actually there's a procedure which describes how you can do it. So implicitly, this is sort of in work of Mosier and Penner, 93. But the sort of self-contained proof, which only refers to the flip graph, is in a paper of Disarlo and Parlier. So this is that's kind of the shortest proof that the flip graph is connected, and that was 19. And basically, the algorithm is saying, well, you need to show that if I give you two triangulations which are not the same, okay, they must have some intersection, then you need to show that there exists a flip I can do which strictly reduces the intersection number. Okay, and then you just keep doing it, and by induction, you can get it connected. So like the main part is like proving that there exists such a flip. Okay, so so this is like reasonably efficient. It's not known whether. So I think it is known that there are examples where it doesn't necessarily give the shortest path. By if you pick the flip which reduces the intersection number the most, I think there are examples which means it doesn't always give you the geodesic, but in practice it seems to be very efficient, and I don't think it's currently known whether this is like a quasi-geodesic. It produces which is like a shortest path up to some additive or multiplicative error. I don't think that's known yet. Okay, but in practice it's quite effective. Okay, so let me do some examples. Sorry. Okay, so in the case of the torus with one mark point, okay, so any triangulation is going to involve three arcs, and it's going to cut up your surface into two triangles. So the arc graph, so every arc can be parameterized by a slope, so a rational number or infinity. Okay, so so let me just draw these ones here. Okay, so these three arcs form a triangulation, so these are adjacent in the arc graph. So I'm drawing a picture of the arc graph here. I can also, so in this picture, I have these three slopes. And what I can do is I can say flip this diagonal here, and I end up with this -1 slope. Okay, so that also gives me a triangulation. So here the triangulations are going to be the maximal simplices, and it turns out that this is just going to be the same as the dual graph of the arc complex. Okay, if you take these maximal things. So if you keep going out, okay, there's always three flips you can do. I can also flip in this edge and replace it by an arc going like that, so that has slope 1/2. Or I can replace this top one here by that slope, which is slope 2. Okay, and I can keep going. Okay, so what we end up with is what's known as the fairy graph. Okay, so the arc graph in this case is going to be the fairy graph, and the flip graph is going to be the dual graph, which is going to be the regular infinite three-valent tree. Okay, so the arc graph in this case is a fairy graph, and the flip graph is going to be the tree. Okay, regular, this thing you see here, going out like this. Okay, and that's kind of like the only picture I can sort of draw where you can see everything. Okay, so this is kind of like the topological side of things. So let me now talk about, okay, triangulations that come up when you have some geometry on the surface. Okay, and so I'll just call these geometric surfaces. Okay, and with some set of mark points. Okay, they might come naturally, or you just might choose to put some mark points on the surface. Okay, so one class of examples are what's known as the translation surfaces. So let me just draw an example. Okay, so translation surface is a type of Euclidean metric you can put on the surface where the transition maps are Euclidean translations. So this is like a very standard example. I can give you a polygon, this L-shaped polygon on the plane, and I can glue these sides, parallel sides, which are equal length and parallel, like so. Okay, so in most places, this will be locally Euclidean, metrically. And if you glue this up, you can check that this becomes a genus 2 surface where the cone angle around here is 6 pi. So if you check, all these points in this picture actually end up being equivalent after the gluing maps, okay, and it will have a cone angle of 6 pi. So this is an example of a translation surface, okay? So I can think of this surface as one of these examples where, well, the underlying surface is just S, and my convention is that I want the singularities to be at least a subset of my chosen set of points. Okay, so so you can add more points if you like, but you would like at least all the singular points to be part of there. Okay, so so what can you do with such a surface? So here, now once you have a geometry, some arcs are sort of better than others. Okay, so for example, if I take this topological arc, so this is a class on the underlying topological surface, but it can be realized by a single Euclidean geodesic segment. Okay, so this is sometimes known as a saddle connection. Okay, but this is like, you can think of like a straight arc or a geometrically realizable arc. The typical situation is something like this. So imagine I have an arc starting here, and it wraps around this sort of cylinder part many, many times, like so. And then if you try to tighten it to a geodesic, what happens is that it actually goes through here and sort of snags along like that. So it breaks up into two Euclidean segments rather than having one. Okay, so generically, you don't expect to have a single arc like this. Okay, generically, like the geodesic representative will pass through maybe several singular points and maybe run over itself many, many times. Okay, so there are some arcs which are straight, some arcs which are not. Okay. Another class of examples, which may be a bit more familiar, would be hyperbolic surfaces. Okay, and I'm going to draw basically the same looking picture. Okay, but there's no sort of natural singularities, but I could just choose a finite set of mark points, okay, as my sort of anchors. Okay, so I can ask the same thing. I can ask for the arcs which are realizable by a hyperbolic geodesic segment connected to such points. Okay, and not every arc can be realized like this. Okay, so there's some. So once you have a geometry, you can sort of pick out some notion of straight arcs. So I'm going to be a bit vague. So we can get straight arcs. Okay, depending on what your flavor of geometry is. Okay, there might be just geodesic segments according to some metric, or there could be some other type of structure where straight makes sense. Okay, but once you have a notion of straight arcs, you can also talk about straight triangulations. Okay, so just the triangulations where all the arcs are straight. Okay, so in the case of a translation surface, you get, so let me just draw another one. So another example of a translation surface is a regular octagon where opposite sides are glued by a translation, and I can just triangulate this, like so. Okay, so that's a Euclidean triangulation of a translation surface. Okay, so in the case where you have like some local Euclidean metric, you're looking at Euclidean triangulations. Okay, I could also have like the arcs going through here because there's some topology, but in this picture, I just kept it simple. Okay, so it turns out on translation surfaces, they always admit triangulations, and you can ask the same thing. Well, is it possible to flip between any two such geometric triangulations? Okay, so let me just do a simple example just to demonstrate that something doesn't quite work. So let's suppose that on my surface, I have two triangles glued like this. Okay, somewhere on my surface I have two Euclidean triangles like this. So so this does form a quadrilateral, but if you try to flip the arc here, okay, I can do this topologically, but if I try to do it geometrically, this thing is not realized by a single segment. So this is not a valid flip. Okay, I cannot convert this triangulation to this one because it's not a geometric one. Okay, so this is kind of like an obstruction to being able to do flips. Okay, so you would like to sort of, naively just do the topological thing, but it doesn't always work. Okay. So, but this is, I guess, quite a, maybe not the topological, maybe not the case of services, but if you look at another situation, which is Euclidean point sets. Okay, so this is not quite, set of points on the surface, but if you're sort of familiar with some computational geometry, this is kind of like one of the things that's quite well studied. You can take a finite set of points on the Euclidean plane, okay, and you can triangulate this set. Okay, so what you're doing is you're kind of triangulating the convex hull, okay, and a classical problem is like, well, if I give you any two triangulations of the same point set, can I relate them by a sequence of flips? Okay, this is something that's quite well studied in computational geometry. Okay, and there is a standard method for being able to connect two triangulations. So, so something which I'm not going to spend too much time talking about, but this is sort of like kind of the triangulation, Delaunay triangulation. It's kind of like one of the main methods for doing flip sequences. So for a Euclidean point set, so what's a Delaunay triangulation? So it's a triangulation where if I give you any triangle, okay, you can consider the circumcircle of this triangle. So the unique circle that passes through those 3 points, and you ask that there are no other points in the interior of the circle. Okay, so you don't want this to happen. Okay, so a Delaunay triangulation is one where this doesn't happen, and if this does happen, well, what can you do? Well, you can consider, well, if this does happen, you can take this quadrilateral and do a flip. Okay, and we had to sort of do it in a careful way, but one property that a Delaunay triangulation has is that it maximizes the smallest angle. Okay, so if you look at all the triangles, look at all the angles you see in all these corners, okay, look for the smallest angle, and amongst all the triangulations, the Delaunay triangulation is the one that maximizes the smallest angle. So it's kind of avoids very, very narrow triangles. Like you want to make the triangles kind of nice and kind of almost regular looking. Okay, so if you had something like that before, if you flipped it, you sort of improved the smaller angle in this setting. Okay, so yeah.
So it's unique?
It's almost unique. So it's unique up to cyclic polygons. So if you have like a bunch of points which lie on a circle, then any triangulation of this pentagon would be Delaunay.
But when you start with two triangulations, you can go to Delaunay?
Yeah. So I have T and T prime. Then the method would be take a path to the Delaunay, take a path to Delaunay. And this is almost unique. Almost unique. It's just up to like if there are no cyclic polygons, then it would be unique. But the lack of uniqueness just comes from just this. Yeah. So this is the kind of like a very, very standard method for finding paths. Find an algorithm that lets you convert a triangulation to a Delaunay triangulation. Okay. And I think, yeah. So this method to convert to a Delaunay triangulation is known. It can run in n² times, quadratic times n being the number of points. But there are examples which say it's necessarily also n². You can't do better than quadratic. Okay, so I think this has possibly been known for a while, but the fact that you can't do better is due to Hurtado, Noy, and Urrutia in 1999. Okay, so you can't do better than quadratic in the number of points. Okay, but this is kind of like the, tried and tested method for flipping between triangulations. Yes.
And for any graph that has a convex hull,
Yeah.
The Delaunay triangulation must exist.
And for any point, so it does exist. Yeah, that's a theorem as well. Yeah. So for any Euclidean point set, you always have a Delaunay triangulation. and like the algorithm terminates. I think that's also a proof that it exists. If you can show the algorithm.
General position. I don't know if they all lie on the line. Then, yeah.
Probably not. Yeah. I probably have to assume that there's nothing. Okay, I guess there must exist a triangulation. So I guess the convex hull can't be degenerate. Yeah. Okay, so Delaunay methods have been applied to these two settings as well. Okay, so there is notions of Delaunay triangulations for translation surfaces and for hyperbolic surfaces. Okay, and this is kind of what people use. So okay, so Smiley and Weiss in 91 showed that translation surfaces admit Delaunay. Okay, which sort of, again, it's not a point set, but you can say that, okay, if you will say work in the universal cover, you can sort of take one of these triangles, and then you can sort of say, does it live inside a Euclidean disk which contains no other points? Okay, so they prove that translation surfaces emit Delaunay triangulations, and you can also flip towards one as well. Okay, so you can flip towards the Delaunay, and we get connected geometric flip graph. Okay, so I didn't say what it means, but it's the flip graph where you only consider the Euclidean triangulations. Okay, I don't know of the the number of steps. I'm not sure what that is or how efficient that is.
And I guess you also need to show that you can connect any two Delaunays by flips.
It's almost again it's almost unique by It's like the lack of uniqueness just comes from very specific configurations. Yeah. So like it's almost unique. So it's kind of like basically you have like a bounded sort of picture here. Yeah. And there's a recent paper by Desprez, Schlenker, and Telot, who did it for the hyperbolic case. So the hyperbolic surface with a finite set of marked points. So they had to do a bit more work. So what they do is they consider looking in the universal cover where you have the point cloud in the disk model, and then it makes sense to define Delaunay by the same circle condition. And it turns out that the circle in the Euclidean hyperbolic is kind of the same because this is a conformal model. Okay, so they proved that Delaunay triangulations do exist, and you can convert a hyperbolic triangulation to a hyperbolic Delaunay triangulation through flips. Okay, so on hyperbolic surface with n marked points, a geometric triangulation, so one made up with hyperbolic edge segments, can be converted to Delaunay using, and there's a bound, some constant that depends on the hyperbolic metric times some constant depending on the given triangulation. So 6g minus 4 times n squared flips. Okay, so this term here is the length of the longest hyperbolic side on the triangulation. So it has finitely many arcs. Take the length of the longest one, and it's to the power of 6g minus 4. This is some constant that depends on the hyperbolic metric. Okay, so it's explicit, but it seems like there should be room to do better, at least to try to make it not depend on the choice of metric. Yes?
What is, could you detail the algorithm used that actually gives you the number of flips?
So for which one?
To get that number of flips.
This one?
Yeah.
Oh, this is very, it's, a lot of detail goes into getting this constant. You need I don't know if okay, so I don't know if the algorithm produces this path, but they can prove that there exists a path. Yeah, like, I mean, it's...
Is this like a type bound? Or?
I don't think so.
Oh.
I don't think so. Yeah, but they have to, like, I mean, what they do is like they really draw the triangles in the universal cover and like compute in the disk model. So that's why like a lot of their bounds depend on how things happen here. So like the methods are very, very specific to doing hyperbolic geometry in this model. So yeah, so it would be nice to sort of not have it depend on very, very geometric quantities. Okay. All right. So, and I should maybe mention one more result by Taha in a recent paper, which generalizes the translation service case. So you can consider any Euclidean cone metric. So in a translation service, the angles have to be multiples of pi or 2 pi, but you could just allow any arbitrary cone angle. So, so he proved that the geometric flip graph for singular Euclidean surfaces is connected. Okay, but his proof was non-constructive. So the argument is that suppose it's false, then look for kind of the smallest counterexample, like in terms of the number of triangulations, and argue for a contradiction. Okay, so there's no way of producing a path using his paper. Okay, so let me now talk about what we do. So this is something we're calling straightening structures. Okay, so I'm not going to give it the definition right now. I want to give you sort of the flavor of the definition and sort of how to think of it and what are the consequences. The definition which involves the maxioms is kind of like the main, I guess, the point of what I want to talk about. So let me just give you the idea. So suppose I have a geometric structure of some sort. So I'm just going to denote it like this. So the surface is marked points, and rho is going to be like a metric or something that gives you some geometry. Okay, gives you some sense of straight line. Okay. From this, if the structure is nice enough, we can try to cook up what we call a straightening structure. Okay, and this is going to be something on the underlying surface, but there's going to be some operator which we just write down as upsilon. Okay, so what's the intuition? Okay, so let's suppose maybe on the surface or on the plane, I have some points, and I consider a topological arc, alpha. Okay, so if I consider tightening this to a geodesic representative, I might get something like this. Okay, so let's call this alpha, and this breaks up into 3 segments: alpha 1, alpha 2, alpha 3. So the geodesic representative is a sequence of these straight segments. Okay, and what I'll do is sort of say, okay, well, the straightening of, so this is an operator which takes in a topological arc and would output some sequence of arcs. Okay, and here I record nothing about the length or angles or anything. It's just like I have a symbol representing each arc, and then I just tell you, okay, symbolically what is, what do I get out? So
what would you do? So go to your bottom vertex between A2 and A3.
Yeah.
And draw a loop basically around sort of the A3 arc.
Okay.
No.
Oh.
Just start at the vertex.
This one?
Yeah, and just draw a circle.
Draw a circle like this. Okay, so in this case, that will sort of run over like that. Okay.
Write it like
So,
A3, A3.
yeah, so this is not how I'm writing it. Okay, this is like this is a sloppy notation at the moment, but sort of gives you intuition. So you want to have like an oriented arc. Yeah. So it's like, it should be, yeah. So if I reversed alpha, I should reverse the letters and the orientations. Yeah. But like, this is like a vague first approximation of what I'm trying to get at. Like the operator should tell you how your, say, oriented arc breaks up into a sequence of straight arcs. Okay, so if you have such an operator, we can say that alpha is straight in some abstract sense if and only if it straightens to itself. So like by definition, if I have some operator which does this, the straight arcs are going to be the ones that are already their own geodesic representative. So for concreteness, you can just think of a translation surface and take the actual geodesic representative and write down the sequence of directed arcs you see. Okay? But once you have a notion of straight, you can then talk about a straight triangulation. Okay? So you can also you can define straight triangulations, whatever they are. So these are the triangulations where all the arcs are like, idempotent under this, whatever this operator is. Okay? And this lets you, define the analogous straight arc graph and the analogous straight flip graph. Okay? So before, when we had these geometric examples, we considered, say, only the Euclidean geodesics or the hyperbolic geodesics. Now just consider all the arcs which are straight under whatever my abstract operator tells you. The triangulations are the triangulations made up of where every arc is straight under this definition. Okay, so I claim that this will generalize these two situations up here. Okay, so that like after I claim that the hyperbolic and the Euclidean settings give you such an operator. Okay, so we have these objects. Okay, so what are our results? Sorry. Okay. Okay, so let me first state it for the arc graph. So suppose I give you a straightening. Okay, suppose I give you some operator which is going to satisfy some axioms I'm going to write down. Then the corresponding straight arc graph is connected and isometrically embedded. In the corresponding topological arc graph. Okay, so this is a subgraph of this thing because I'm only taking some of the vertices and taking the induced graph. Okay, it turns out the embedding preserves distances. Okay, so so this is in the case of translation services, this is a result that's already known. So Minsky-Taylor in 17 proved that this is true for translation services. And sort of the axioms of the straightening operator is kind of modeled on some of their results to sort of make this work. So the proof is not too much different. Like a lot of their stuff goes through if you sort of axiomatize it a bit. Okay? And secondly, we have the corresponding result for the flip graph. Okay, again, under the same assumptions. Okay? So the flip graph, the corresponding flip graph, first is, well, I should say it's a non-empty first, which is actually a non-trivial statement, that there already exists triangulations where all the arcs are abstractly straight, connected, and moreover, okay, I could talk about the embedding, but let me just write it down a bit more explicitly. Given any two straight triangulations, the distance in the straight flip graph. So I have a subgraph in the topological one. I can measure the distance here between these two triangulations. This is bounded above by some constant times the distance in the topological flip graph. Okay, and I'll say a bit more about the constant. So this constant depends only on the topology, and in fact this is quadratic in the triangulation complexity of the surface. So it does not depend on any of the geometry at all. Okay, the only dependence on the genus and the number of mark points. Okay, so there's some multiplicative constant here. So you could connect two triangulations in like the hyperbolic or the Euclidean settings in basically almost the same efficiency as you can do it in the topological one, like by some multiplicative error. Okay, and here it does not depend on any metric or anything at all, just on the topology.
Can you give us a definition of epsilon in the case of translations?
I will. So I'm going to give you the definition. Okay, so yeah. Okay, but this is like the statement of what it can do, and then so when do I go to? 5.2. Okay, so maybe I'll just write down the definition. Okay. Okay, so in order to define it, it's more convenient to work upstairs. Okay, so you would like to work in a universal cover, but because we have marked points, we have to be a bit more careful. So if I give you the surface downstairs, I want to be able to talk about arcs and triangulations down here. Then what you can do is you can consider the Ferry complex. Okay, which is this simplicial complex you get by just taking a triangle and just gluing more and more things here. Okay, so I'm drawing a different picture to what I had before because you might be used to thinking about the Ferry tessellation, but this picture, even though it kind of looks the same, is kind of geometrically misleading. Okay, I really want it to be the topology of a simplicial complex which makes the vertex set discrete. Okay, in this picture, the vertex set would be not discrete there. So that's the wrong topology. So with this topology, you get an infinite branch covering of from here to here. So how you can do is I can just triangulate it any way I like down here. Okay, so and I pick some triangle down here and I just say this triangle maps to this one. And every triangle has three neighbors like locally. So you can say, okay, well, this triangle is going to glue to the whatever triangle is down here. Okay, so you can combinatorially define a map from the Ferry complex to any triangulated surface. Okay, and this is going to give you an infinite branch covering where the vertex set is going to descend to the set of mark points. So I'll denote it like this. Okay, and it kind of acts like a universal branch cover. Okay, so this what I've done right down here depends on the choice of triangulation, but it turns out it doesn't really. So in a sense, if I give you any other branch cover of this surface with discrete set of mark points, then there's a unique way that this thing factors through. Okay, so you can think of this as a universal branch cover. Okay, the point is that I can construct this topological space that depends only on this. Okay, and it's homeomorphic to the Ferry complex. So what is this useful for? Well, if I want to talk about an arc on this surface here, then a lift of this arc would be some arc connecting some pair of these mark points up here. Okay, so every arc is determined by just a pair of points in Z. Okay, so I can forget about just the topology and just remember the set Z. Okay, so that's what I'm doing. So I should also remark that the fundamental group of the punctured surface acts on this by deck transformations. Okay, so you don't have a unique arc, but you have like an orbit of arcs, sort of in the same way as you would do for the universal cover. Okay, so the main point here is that okay, this picture is kind of like maybe geometrically accurate, but here we can see that the set Z is cyclically ordered. Okay, since it lies on the circles, that's the thing we want. So a straightening structure is going to be some operator on a cyclically ordered set. Okay, so let me write down the definition. So So we call a straightening system is a cyclically ordered set that's denoted by x comma that equipped with an operator. Which we call a straightening operator. Okay, and what's this going to do? It's going to take pairs of elements in a set, so just think of like endpoints which represent arcs, and it would output a non-empty string on that set. Okay, so let me give you an example to sort of see what, maybe I'll just erase this so we can see an example. Okay, so I'm drawing a very jagged polygon, just to sort of emphasize what's going on. So here, it's a cyclically ordered set. I just take the corners to be my set, okay? And let's suppose I give you 2 elements, okay? So if I input 2 elements, I want to give you some non-empty string. So intuitively, I'm imagining taking this arc and then pulling it tight. So it'll go like this. Maybe not like that, like this, okay? So then I just write down that sequence of points I see. So this would be like x0, x1, x2, x3, x4, x5, x6. Okay, so my operator would eat this pair x and y and give me this string x0 up to x6. Okay, so it's just a sequence of elements. So the elements of the set are just the corners. Okay, and it's going to give me something like this. And I'm going to refer to anything that you can get from here as an elected path. Okay, so for any pair, the operator chooses some sequence which starts from the first one and ends at the last one.
Would this sequence always be the convex hull of the
I mean, in this example, it's just because I chose it to be geometric, but it's purely abstract. In the definition, there was no reference to geometry at all. It's just a cyclically ordered set and some operator. So there's no, a priori, there's no geometry. Okay? So, okay, and then such that. Okay, so the first one is that.
So the point where you've used the cyclic order is when you write down the sequence of points xi?
No. So this can be in any order. But the cyclic order is going to come in one of the axioms I'm going to write down. Yeah. Yeah, so it hasn't appeared yet. It's just a set, and I'm just checking strings. Okay. Yeah, so there's no cyclic order yet, but there will be cyclic order when I write something down. So first is that if this operator outputs this string, okay, and n can be allowed to be maybe one symbol, then x0 equals x, xn equals y. So that's just saying it starts and ends at the given 2 points. The second one is symmetry. So if I reverse the order, then I just get the same sequence but in reverse. So I'll just write it like a bar. Okay, so it just goes back and forth. So intuitively, these axioms are going to model how a geodesic representative of an arc behaves. Okay, so this is symmetric. The next one is a global to local property. So any subpath of an elected path is elected. So in this picture, if I pick any 2 vertices that appear along this one, then the upsilon is going to give me this subpath. Okay, this is like saying subsegments of geodesic are also geodesic. Okay, the next one is a local to global one. Okay, so if I give you some path satisfies each segment of path length 2, each subpath of length 2 is elected, okay, then this is also elected. So it's saying that a geodesic can be detected just by seeing if it's locally geodesic. So if I check, is this geodesic, is this geodesic, and so on. If I can check that every subpath of length 2 is elected, then the whole path is also elected. So testing for geodesicness is like a local test. And finally, we have one which uses the cyclic order. And let me leave that there. So maybe I'll do here. Okay, so the one which uses the cyclic order is the one which captures non-positive curvature. Okay, so, and we call this the linking property. So which says if I give you two such things, so for all x, y, x prime, y prime, okay, if an arc along this path, elected path of x to y, crosses an arc along the elected path of x prime to y prime, then the original arcs had to cross. The arcs, then arcs xy and x prime, y prime cross. Okay, so what does that mean in terms of the cyclic order? So maybe I'll just do it in this picture. So I can give you another let's say I take this one to be x prime, and let's say I take this one to be y prime. Okay, so these two arcs in the cyclic order do not cross. Like their endpoints do not link in infinity. So if you look at the cyclic order, you don't alternate between the endpoints. So the sort of converse of this says that there should be no arcs along the purple one that should cross the red one. So when you straighten it, it looks something like this. Okay, so they're allowed to run over the same things, but there are no trans. Okay, so maybe in the case of a hyperbolic, maybe if you imagine the hyperbolic plane, if I give you one geodesic here and another geodesic here, where the endpoints don't cross, then the geodesic between them cannot cross. You cannot have this thing happening. Okay, so this is kind of like a very abstract way of describing the non-positive curvature. Okay, so in the Minsky-Taylor paper, they proved that for translation services, that this property is true, that the linking property, whenever you have two arcs that topologically don't cross, when you take the geodesic representatives, there are no transverse intersections. Okay, and what this last axiom is doing is just modeling what they did. Okay, so yeah. Okay, and finally, the definition of a straightening structure is one which is equivariant under the deck transformation group. Okay, so you define it up here. If you have an equivariant operator, then it descends to one where it makes sense on the surface, and that's our definition of a straightening operator. Okay, so, and yeah, the case of the translation services and hyperbolic services we show they satisfy these axioms. So therefore, this result applies to those cases. Okay, so I think just stop.